Given the Black-Scholes-Merton theorem, we are now ready to price options. We will start from one of the simplest situations, that is to say, the European call. Now, a European call is a very simple and standard type of option. It's an option that gives us the right, but not the obligation, to buy an underlying asset at a predetermined price at a given time in the future, that is to say, at maturity. So in a European call, there are three main quantities that are important for us. One is the time horizon, that is to say, for us is the interval 0 capital T. The second element is the so-called strike price, that for us is the quantity K. The strike price is a price that it is defined by the two counterparties of the contract, the buyer and the seller. So is a reference price on which the two counterparties agree. And finally, we have the price of the underlying asset. So there is a stock, for example, that we are following over time in its price behavior, and what we will do is to observe, to try to model in reality what will be the price at maturity. So if I buy a European call, today in day 0, the two counterparties of the contract, that is to say me, the buyer, and the seller, will decide what is the capital T, so the maturity of the contract, and will set the strike price K. That will be our reference price. This is the price that essentially will tell us if our call is profitable or not for each one of us. Obviously, we will have different perspectives. What is important is that in a European call, I buy as buyer the right but not the obligation to buy the underlying asset at the strike price. But I can only exercise my option at time capital T. So in a European call, the right of the option can be exercised only at maturity. This is important because this is a fundamental difference, for example, between the European call and the American call. In an American call, I can exercise my right at any time between 0 and capital T. This little difference we will see, in particular when we consider puts, has a tremendous impact on the modeling of and the pricing of the different options. So for us, in the very basic setting we are considering, what we have is that we have our European call, so we have set at maturity capital T, we have set a strike price K, and we follow the price of the underlying asset that, as you can imagine, is modeled as a geometric running motion. What we want to find is the value of such an option at any time t between 0 and capital T. This will be what we are looking for in order to price our option. To introduce some extra terminology, when we are at maturity, so at time capital T, we say that our option, and we are taking obviously the perspective of the buyer, so our perspective, is in the money if S capital T is strictly larger than K. So if it is meaningful to me to exercise the option because I can immediately buy the asset at a lower price, the strike price, and I can have a profit because I can immediately sell it back at the higher price, so the actual price on the market, which is S capital T. We say that the option is at the money when S capital T is equal to K, so when the price on the market is equal to the strike price. In that situation, if you want, I can exercise the option but the price is exactly the same price as the strike price, so there is no particular gain in exercising the option. And I say that the option is out of the money when, on the contrary, S capital T is smaller than the strike price. In that situation, it is not particularly clever to exercise the option if I'm just interested in the payoff of the option. So we start by considering our European call option, which is a function of the price of the underlying asset at maturity at time capital T. This function is a function that takes the maximum between 0 and the difference between the price of the underlying asset at maturity and the strike price K. Following Black-Scholes, we then have that the value Vt is equal to the discounted conditional expectation at time t of the value of the option at maturity that corresponds to Fs capital T. Then we just have to substitute for S capital T by taking into consideration what we know about the geometric Brownian motion when we consider the time interval small t and capital T. Please notice that we are operating under the risk-neutral measure. Under such a measure, the process Wt is a standard Brownian motion, so the future increment W capital T minus W small t is independent from the filtration stopped at time small t. Moreover, we also know that the price process St is Ft measurable. Therefore, the conditional expectation reduces to a standard expectation. What we do is now to introduce the function ftx, just to simplify a little bit the notation. It is quite evident to observe that the value vt is nothing more than f as a function of t and st. We then observe that the increment of the Brownian motion over the interval t capital T is nothing more than a normally distributed random variable with mean 0 and variance equal to the difference between capital T and T. This allows us to rewrite the expectation, that is to say the function capital F, in terms of an integral involving a normally distributed random variable. And this fact will be extremely useful in what follows. So let's go back to the expectation representation and let's substitute for the payoff of our option that involves the maximum function. Such a maximum is between the difference between the price of the underlying asset at maturity and the strike price and 0. Therefore, what we can verify is under which condition the argument of the expectation is non-negative. We call the argument of the expectation capital A, and then we can solve for which values of the normally distributed random variable z such an argument is non-negative. This allows us to obtain the quantities d1 and d2. The definitions of d1 and d2 that you find in the lecture notes are just to be consistent with what you find in books or in many papers and even on Wikipedia, but it's just a matter of convention. Actually, if you see and if you try to solve for A, for the quantity A, for the expression A to be non-negative, then you find that the actual condition is Z being larger than equal to minus D2. So in principle, you could take the minus within D2, rearrange the terms, and call that quantity D1 or D2, or as you prefer. So since I want to be in line with what you find in other places, in other resources, on the book by Shreve, this is why I use this notation, even if I understand it can be somehow counterintuitive. Now, if we introduce the indicator of the event z being larger than equal to minus d2, we have that we can rewrite the expectation as you see on your screen, because that event guarantees that the argument capital A is non-negative. After that, we can just rewrite the expectation in terms of integral involving a normal random variable, and exploiting the symmetry of the normal distribution, what we can do is we can switch the limits of integration from minus d2 until plus infinity to minus infinity d2. This simplifies our representation in terms of CDF, cumulative distribution function, of the normal distribution. In fact, if we now split the integral into two parts, one in x and one in k, and we apply a very simple change of variable, we can now write our function capital F in terms of the difference of two CDF of a standard normal computed in D1 and D2. Now, it comes just by substituting x with st, that the value in t of a European call is equal to st capital phi in D1 minus k times e to the minus r capital T minus t, which is our quantity tau, multiplying capital phi d2. This is the value of a European call at time t between 0 and capital T. If you are conversely interested in the modeling of an European put, the procedure is essentially the same, so you can really mimic the steps that we followed together for the European call. The main difference is the type of option, the type of contract that we are considering now. In a European put, if you are the buyer, you buy the right but not the obligation to sell the underlying asset at a predetermined price, the strike price. So it is clear that the payoff of a European put is different. It is no longer the maximum between st minus k and 0, but conversely it will be the maximum between k minus s capital T and 0. For the rest, once you substitute the payoff, you can just follow the procedure and the steps we have considered together. And I leave the pricing of a European put to you as an exercise. I would like to conclude this video lesson by starting a discussion that we will continue in the next lessons. That is to say, the discussion about volatility, about the sigma parameter of our Black-Scholes-Merton construction. Now, with the change of measure from P to Q, we are able to get rid of the drift problem. So we are able to substitute the drift with the risk-free rate, and that solves all the things we have already said. What remains as parameter to be studied, to be estimated, and to be understood is sigma, the volatility. Now, as we shall see, sigma has a very important role in the construction of the Black-Scholes-Merton universe. And I will try to show you not only how sigma can be estimated and how it can be used, for example, to evaluate if an option is more profitable than another, if an option is riskier than another, but I will also try to show you that sigma is actually the parameter that governs, at least up to a very big part, the distortion that we introduce every time we move from P to Q or back from Q to P. Now, the first thing that I want to discuss with you in terms of sigma, in terms of volatility, is how we can estimate this quantity. Because since this quantity is still there and we are not getting rid of the quantity by substituting sigma with something else, as we do with nu, with the drift, it is important that we know how to evaluate sigma, because it's fundamental, for example, for pricing purposes. Our pricing formulas depend on sigma, so it's a parameter that we need to master. There are many approaches in the literature. but the two main ones are the historical approach, so the historical volatility approach, and the implied volatility approach. We start with the first, with the historical one. In the historical volatility approach, we use past data taken from the market, for example, taken from the time series of the prices of the asset that we are considering, in order to get a statistical estimate of the volatility. In order to do that, we will exploit the properties of the geometric Brownian motion, which is the process that we are using to model the behavior of prices. And even more, we will exploit fundamental properties of the Brownian motion. In particular, in the historical volatility approach, we need the quadratic variation of the Brownian motion. So, what I ask you is to refresh your knowledge of the quadratic variation. In the lecture notes, you find some details, but I will not cover that part. So this is left to you, because I assume you already have this knowledge from the other courses within the specialization in financial engineering. In the historical volatility approach, so as I was telling you, we use past data. Now, this approach, as you will see, is rather simple. So it's very simple to obtain the formula that we will use to estimate volatility. But it's very important to stress one thing. It's an historical approach, so it relies on historical data, on past data. A fundamental assumption that we are making, and which is more or less the assumption that we always make when we use past observation, is that the past is a reliable, if not an optimal, predictor of the future. It means that in the future we can expect things that we have seen in the past, and that if we have enough observations from the past, our forecasts about the future are reliable. Now, you can imagine that this type of approach is prone to what is known as historical bias. Historical bias is when you over-rely on the past to forecast the future. Now, one thing that I like to stress is always that the future, and it can be proven, is fatter-tailed than the past. In sports, when we look at sports, when, for example, we look at the world record in running or in any other type of sport performance and discipline, we know that the new record, so the new speed limit, is never in the past. It's something that belongs to the future. In finance, sometimes we forget about this, and we tend to behave as if what we have seen so far is all that we can see. This is highly dangerous. If you have not yet observed the default of Lehman Brothers, it does not mean that that default cannot happen in the future. So, historical volatility is a nice approach, it works, but it needs to rely on good market conditions, for example. In good market conditions, when we can expect that no particular large variations, large deviations in the prices are there, and so if in the prices, also in the returns are there, then the historical volatility approach works. But during a crisis, for example, I would not suggest using that approach. As you will see, the more we enter into the content of the course, the more I will start criticizing parts of the approaches that we use. And later in the course, for example, I will also try to stress that Black-Scholes-Merton is not the only way that we can use to price a European coal or a European put or any other type of option. There are alternatives, and I will try to give you a quick overview of the alternatives, because it's always nice not to restrict all your knowledge to just one approach. But now let's go back to the analysis of volatility, and let's quickly say something about the historical volatility approach. But please remember historical bias. Historical bias is a potential risk when you use historical volatility. If things go well, very nice, but if they go bad, then it can be risky. You can introduce a lot of model risk into your framework. As usual, we use a geometric Brownian motion to represent the price process, and we assume that we observe prices over a time interval capital T1, capital T2, which is included in our horizon of events, that is to say 0, capital T. Now, for this interval, we consider, as before, a partition whose mesh vanishes, so the mesh of this partition tends to 0. Then what can we do? For all the small increments, we can compute the log returns. And by taking the sum of the squares of the log returns, we can compute what is known as the realized volatility by practitioners. This realized volatility, as we have just said, is nothing more than the sum of the squares of the log returns. So what we can do? We can expand the squares, and this allows us to write the realized volatility as the sum of 3 different elements, A, B, and C. Using the quadratic variation of the Brownian motion, we can immediately see that the quantity capital B is more or less equal to sigma square times the length of the time interval we are using, the time interval that we are using to observe the prices, that is to say, the one between capital T1 and capital T2. For what concerns, conversely, both A and C, it is easy to verify that these quantities are both equal to 0, so they disappear. It means that we can rewrite our realized volatility only in terms of the term capital B. Now, it is just a matter of rearranging everything to find out that the variance sigma square is equal to 1 over the interval length between capital T1 and capital T2 and the sum of the squares of the log returns. Now, if we observe the log returns, so if we observe the time series of prices and we can compute the time series of the log returns, then using the formula you see on your screen, it is very simple to compute the empirical variance, and once we have the empirical variance, we can just take the square root and we will have the empirical standard deviation, that is to say, our volatility using the historical volatility approach. It is important to stress that in the historical volatility approach, not only we are requiring to have past observation and we are prone to historical bias, but the quality of the partition we are considering is fundamental. The finer the partition we can take into consideration, the better our estimate. So if we consider weekly observations, we will have a rather poor estimate of the volatility. If we use hourly or intraday observations, we will have a much better estimate of the volatility. The compromise, as usual, is between the quality and the quantity of the data.